Hello and welcome to yet another Korean College Scholastic Ability Test video. This particular problem here is the problem number 30, which is the very last problem of this year's test, which was held only a couple of weeks ago. So let's take a look at the problem itself. fx is a cubic function with positive leading coefficient satisfying f3 equals 1/2 and f'3, the value of derivative, equals 0. Gx is defined as e to the sine pi x minus 1. Hx is defined as g of fx for all real numbers x. Then, this function hx satisfies the following conditions. Condition A, at x equals 0, hx has a local maximum value of 0. Condition B, the equation hx equals 1 has 7 distinct real roots in an open interval 0, 3. Then f2 equals q over p, where p and q are co-prime natural numbers. Find the value of p plus q. This p plus q thing is just to make the answer natural number, so the important part is that we have to find the value of f2. And of course, in order to find f2, we must find the cubic function fx. And in order to find fx, we have to take a closer look at given conditions, including the conditions with gx and hx. So first, let us take a look at the problem again to extract some simple clues that we can find from here. First, it says fx is a cubic function with positive leading coefficient, so we can write it as ax cubed plus bx squared plus cx plus d, where the leading coefficient a is positive. Next, hx is defined as g of fx, so using this given gx, we know that hx equals e to the sine pi fx minus 1. Next, let us actually take a look at this first condition of hx. It says hx has a local maximum 0 at x equals 0. This actually tells us two things. First, we know that h0 equals 0. Second, we know that because hx is local maximum at x equals 0, we know that the derivative of hx at x equals 0 also must be 0. So let us take a closer look at these two conditions. So hx, which is g of fx, is given like this. First, h0 equals 0 means that e to the sine pi f0 minus 1 equals 0. So e to the sine pi f0 equals 1. Therefore, sine pi f0 equals 0. At what value of f0 does sine pi f0 become 0? The best way to solve this is to use the graph of the sine function. From this graph of y equals sine pi t, we know that the period now becomes 2. You can notice that y equals 0 at t equals n, where n are integers. Therefore, we have f0 equals n, where n are integers, and we already know that from fx equals ax cubed plus bx squared plus cx plus d, f0 equals d, so we have d equals n. So let us just replace d with n to remind that it is an integer. Next, the derivative condition, h'0 equals 0. Here we have to take derivative of this function, and we have to use the chain rule, so the derivative h'x is given as first e to the sine pi fx, then we have to take derivative of sine pi fx, so we have to multiply cosine pi fx, and we have to take derivative of pi fx, so we have times pi f'x. Therefore, h'0 equals e to the sine pi f0 times cosine pi f0 times pi times f'0, which must be 0. Here, this e to the sine pi f0 actually equals 1 from the conditions that h0 must be 0, but even if we don't use this exact value, we still know that this term is positive. So this term cannot be 0. Moreover, from h0 equals 0, we have also established that f0 equals n, which is an integer. So we know that this cosine pi f0 equals cosine n pi. And from this graph of y equals cosine pi t this time, which also has the period of 2, you can see that value of cosine n pi is either 1 or minus 1, So this term also cannot be 0. Therefore, the only thing that can be 0 here is this f prime 0. Now from here, we know that this f prime 0 equals c, the coefficient of x. Therefore, we have c equals 0, so we have fx as ax cubed plus bx squared plus n. Before we move on, let us actually use the fact that hx has local maximum at x equals 0. This part, h prime 0 equals 0, merely reflects the fact that hx has local extremum at x equals 0, which can be either local maximum or local minimum. In order for this hx to have local maximum at x equals 0, the graph of hx around x equals 0 must look like this. It must increase, then decrease. Therefore, the graph of its derivative h prime x must look like this. It must go from positive to negative. From here, we know that e to the sine pi fx is positive, and f prime x is a convex quadratic function with f prime 0 equals 0, and f prime 3 equals 0. Yeah, we also have this condition. Therefore, this f prime x changes from positive to negative when passing x equals 0. So in order for the graph of h prime x to go from positive to negative, the logical conclusion is that this cosine pi fx must be positive at the vicinity of x equals 0. Or you can say that cosine pi f0, which is cosine n pi, must be positive. We've seen that this value is always 1 or minus 1, but more specifically, cosine n pi equals 1 when n is even, and equals to minus 1 when n is odd. Therefore, in order for this cosine pi fx to be positive around x equals 0, this value must be 1, hence n is even. And this is the important information we can deduct from this local maximum value condition. Now with these conditions established, let us take a look at our cubic function fx again. From this expression, we know that its derivative f prime x equals 3ax squared plus 2bx, which is x times 3ax plus 2b. So this one definitely gives f prime 0 equals 0. And from f prime 3 equals 0, we have 3 times 9a plus 2b equals 0. Therefore, b equals minus 9 over 2a. This gives fx as ax cubed minus 9 over 2ax squared plus n. And we also have this condition, f3 equals 1/2. So we have f3, which is 27a minus 81 over 2a plus n equals 1/2, which gives a as 2n minus 1 over 27. Therefore, if the value of n is determined, then we can use this relation to determine the value of a. Now perhaps the most important part, the graphical features of both fx and its derivative. From here, we know that the graph of the derivative y equals f prime x is a convex parabola passing through 0, 0 and 3, 0, which correspond to the local maximum and local minimum of fx respectively. Therefore, the graph of the cubic function y equals fx looks like this. At x equals 0, it has the local maximum, which is even number n, and at x equals 3, it has the local minimum, which is 1/2. Now with these established, let us now take a look at the second condition for hx, that the equation hx equals 1 has 7 distinct real roots in an open interval 0, 3, which happens to be the interval between local maximum and local minimum point of fx. Now let's use this expression for hx. If hx equals 1, this equals 1, so e to the sine pi fx equals 2. Therefore, sine pi fx equals ln 2. So equation hx equals 1 is equivalent to sine pi fx equals ln 2. And this is where I draw the graph of y equals sine pi t again, which I gotta admit looks pretty ugly, but that's not the point. Notice that ln 2 is greater than 0 but less than 1. So if we draw the horizontal line y equals ln 2, it intersects our sine graph like this. And one of the values of t that satisfies sine pi t equals ln 2 is this x-coordinate, which we will call k. Well, actually k have this exact expression, but who cares, right? Let's just simply call it k. Then, as you see, this k is in between 0 and 1/2. And this k is not the only value of t that gives sine pi t equals ln 2. There are also these values. From the symmetry of the sine graph, you can see that the coordinates are 1 minus k here, then 2 plus k and 3 minus k here, and 4 plus k and 5 minus k here, and so on. Therefore, if sine pi fx equals ln 2, then fx can have values of k, or 1 minus k, or 2 plus k, or 3 minus k. Then we have 4 plus k, 5 minus k. Let's actually write down more values here. 6 plus k, 7 minus k, 8 plus k, and so on. There are values also at the negative side, of course. Now let's bring back our cubic function fx with local maximum n and local minimum 1/2. Since k is in between 0 and 1/2, the line y equals k must be located here below 1/2, and the line 1 minus k must be located here above 1/2. And now we're ready to interpret this condition graphically. hx equals 1 having 7 distinct real roots between 0 and 3, where the graph of fx strictly decreases, means that fx must have 7 different values among these, which also must be greater than 1/2. And these 7 values must be, the first one is obviously this 1 minus k, then 2 plus k, and 3 minus k, 4 plus k, 5 minus k, 6 plus k, and the 7th one, which is the last one, below this local maximum value n, must be 7 minus k, and the next one, 8 plus k, must be above n, so that these x-coordinates of the 7 intersection points are the 7 distinct real roots in the aforementioned interval. And this graph finally gives us the value of n. Notice that 7 minus k is here and 8 plus k is here, so n can be either 7 or 8. But we have already shown that n must be even, from the previous local maximum condition. So n equals 8. So we have finally obtained the value of n. Therefore, we have n equals 8 here, and using this previously found relation between a and n from the condition f3 equals 0, a equals 2 times 8 minus 1 over 27, which is 15 over 27, which is 5 over 9. Therefore, fx equals 5 over 9 x cubed minus, then we have 27 over 2 times 5 over 9, which gives us 5 over 2 x squared, then plus 8. The problem asks us to find the value of f2, so f2 equals this, so first term is 40 over 9, and the second term becomes 10, then we have plus 8, so we have 22 over 9. This equals q over p, therefore p equals 9 and q equals 22. Therefore p plus q equals 9 plus 22, 31. And this is our answer. Alright, so this was another challenging Korean college scholastic ability test problem. You had to have a solid understanding about the relation between the derivative and the function having local maximum at certain point, and also about the graphical meaning of equation having certain number of roots, and also about the basic periodic properties of the trigonometric function. If you want more of these kind of problems, please check the link in the description, and also please press that like and subscribe buttons and enjoy many more upcoming videos. And as always, I will see you in another video.